A telescope has just exposed something that shouldn't be possible. The universe we believed spanned 14 billion light-years is now understood to stretch nearly 93 billion light-years across. When the James Webb Space Telescope focused on what appeared to be an empty patch of sky, it uncovered more than 800 galaxies concealed in the darkness, galaxies that formed when the universe was only 300 million years old. Black holes billions of times more massive than theory allows. Vast structures stretching tens of millions of light-years, existing when there simply wasn't enough time for them to form. Everything we thought we knew about the universe's size and its history has been shaken. If you're ready to see what's really out there, like, subscribe, and let's begin. Light does not arrive instantly. When you look at something 1 mile away, you see it as it was 5 microseconds ago. When you look at the moon, you're seeing it 8 seconds in the past. The nearest star appears as it was 4 years ago. This is not speculation, it is fundamental physics. Every photon traveling through space carries a snapshot of the moment it began its journey, turning the universe itself into a vast time machine. The James Webb Telescope sits 1 million miles from Earth, staring into darkness. Its mirror stretches 21 feet across, coated in gold to catch infrared light. Infrared is what remains after visible light has been stretched by the universe's expansion. Think of it like a siren passing you on the highway. The sound drops lower as distance grows. Light does the same thing across cosmic distances. Webb isn't just looking far away, it's looking backward through time itself. The most distant galaxy it found emitted its light 13.5 billion years ago. That means we're seeing this galaxy as it appeared when the universe was only 290 million years old. For perspective, if the universe's age was compressed into 1 year, this galaxy formed on January 20. Here's what makes this extraordinary. The light traveling toward us has been moving through space for almost the entire history of existence. When that light began its journey, Earth didn't exist. Our star hadn't formed. The Milky Way was still assembling itself from cosmic gas. Dinosaurs, humans, civilization, everything we know came and went while these photons crossed the void. Every image Webb captures is a fossil, a preserved moment frozen in light. The telescope gathered photons for almost 10 hours to capture one ancient galaxy, 10 hours of collecting light that has been traveling for 13.2 billion years. The patience required is staggering. Scientists used an instrument called a spectrograph to confirm the distance. This device splits light into its component colors like a prism, creating a rainbow. Specific patterns in that rainbow reveal how fast the universe has been expanding since the light was emitted. The farther away something is, the more its light has been stretched. This galaxy showed a redshift of 14.32, the highest ever recorded for a confirmed galaxy. What this means for us: we're not just observing distant objects, we're witnessing the universe's childhood. We're seeing the first structures that would eventually lead to everything we know. Every star, every planet, every atom in your body can trace its origin back to these early moments. But distance creates a problem scientists never anticipated. The galaxy has a name that sounds like a serial number: JADES, GSZ14-0. Scientists spotted it in October 2023, then spent months doubting what they saw. It appeared too bright, too large, too developed for something that shouldn't exist yet. When astronomers pointed Webb spectrograph at this galaxy in January 2024, they confirmed their suspicions. The object sits 13.5 billion light-years away, formed just 290 million years after the Big Bang. That puts it in an era called cosmic dawn, when the first stars were supposed to be flickering into existence, emphasis on supposed to be. Here's the problem. This galaxy measures over 1/600 light-years across. That's tiny compared to modern galaxies, but enormous for its age. It contains several 100 million times the mass of our Sun, all packed into young stellar populations. The light comes from stars, confirmed by spectral analysis, newly born stars blazing with ultraviolet radiation. Theoretical models predicted early galaxies would be small, dim, simple collections of a few million stars at most. The universe, at 290 million years old, shouldn't have had time to build anything substantial. Gravity works slowly, gas collapses gradually, stars form over millions of years. Dark matter halos need time to accumulate enough material to seed galaxy formation. Yet there it sits, bright enough that Webb could detect it even if it were 10 times fainter. That detail terrifies astronomers because it suggests this galaxy isn't alone. If one exists at this distance, dozens more probably hide in regions Webb hasn't surveyed yet. The team found a second galaxy nearly as distant, labeled JWST 14-1. Two record-breaking galaxies in the same field of view, both showing properties that contradict standard cosmological models, both producing starlight at rates that should be impossible. What makes researchers especially uneasy is the composition. Spectral lines revealed not just hydrogen and helium, but heavier elements. Carbon, oxygen, nitrogen. These atoms only form inside stars, then spread through space when those stars explode. That means an earlier generation of stars must have already lived and died before this galaxy formed. The timeline keeps getting pushed backward. One astronomer described finding this galaxy like excavating a smartphone among ancient Roman ruins. The technology is too advanced for its era, the structure too sophisticated, the brightness too intense. This discovery forced scientists to extend humanity's view into the cosmic past by 40% during Webb's first 18 months of operation, 40% deeper into time than we'd ever seen before. The question nobody can answer: if galaxies this massive existed this early, what else are we missing? Here's where the universe stops making intuitive sense. Light travels at 186.0 miles per second. Nothing moves faster. This is confirmed by every measurement we've ever made. In 1 year, light covers about 6 trillion miles. Multiply that by the universe's age of 13.8 billion years, and you get how far light can travel since the Big Bang. The answer should be 13.8 billion light-years. Simple math, except that's completely wrong. The actual edge of the observable universe sits 46.5 billion light-years away in every direction. The total diameter measures 93 billion light-years across. We live in a sphere of space nearly 7 times wider than the distance light could possibly travel in the universe's lifetime. This isn't a mistake, it's expansion. Space itself is stretching. Imagine drawing dots on a balloon, then inflating it. The dots move apart even though they're not traveling across the balloon's surface. The surface between them is growing. Space works the same way. Galaxies aren't flying through space. Space is carrying them apart. When a distant galaxy emitted light 13.5 billion years ago, it was much closer to us than it is now. That galaxy has been moving away from us the entire time its light traveled toward us. By the time that ancient light reaches our telescopes, the galaxy that emitted it has drifted to a current distance of 46 billion light-years. Think of it like running on a treadmill towards someone standing ahead of you while you run forward. The treadmill pulls you backward. You might eventually reach them, but they'll be farther away than when you started. Light does the same thing, fighting against cosmic expansion. Here's what makes this deeply strange. Regions of the universe exist beyond 46.5 billion light-years. We know they're there because space extends infinitely in all directions. The observable universe is only the portion where light has had time to reach us. Beyond that boundary, galaxies shine, and stars explode, and planets orbit. We just can't see them. We never will. The expansion rate is accelerating, confirmed by observations of distant supernovae. This acceleration is caused by something called dark energy, which comprises 68% of everything that exists. Dark energy's density remains constant as space expands, which means its total amount increases as the universe grows larger. What this means: the universe is simultaneously finite in what we can observe and infinite in what actually exists. Every second, the edge of what we can see grows larger, but space itself grows faster. Distant galaxies are disappearing beyond our reach. And stranger still, the rate of expansion seems to be different depending on where we look. Webb stared at a patch of sky slightly larger than 3 full moons for 250 hours. The region is called the Cosmos Webb Field. When Hubble examined this same area, it found roughly 10 zero galaxies. Scientists thought that represented a complete census. They were wrong by a factor of 80. The final Webb image contains 797, 942 galaxies, nearly 800, zero distinct collections of stars, each containing billions or trillions of stellar masses. The photograph required combining more than 10 zero individual exposures, carefully aligned and corrected for observational errors. To understand the scale, picture printing the famous Hubble ultra-deep field on a standard sheet of paper. The Webb image would need to be printed 13 feet tall by 13 feet wide at the same level of detail, wall-sized mural of cosmic history. Every single galaxy in this image tells a story. Some formed 12 billion years ago when the universe was young and chaotic. Others took shape relatively recently, just a few billion years back. The catalogue includes measurements for each galaxy's distance, brightness, mass, and star formation rate. Scientists can now track how galaxies evolved across 98% of cosmic time. What makes this image revolutionary isn't just the number of galaxies, it's the distribution. The galaxies aren't scattered randomly. They cluster along invisible threads. They gather at intersections. They avoid certain regions entirely. The pattern reveals the cosmic Weber large-scale structure of dark matter filaments, connecting every major mass concentration in the universe. Webb's infrared vision pierced through cosmic dust that had hidden entire populations of galaxies from previous surveys. What appeared empty, invisible light blazes with activity in infrared dusty regions where new stars form, ancient galaxies whose light has been stretched into wavelengths human eyes can't detect. Objects Hubble literally couldn't see. The team spent years developing technology to measure properties of 800 zero galaxies simultaneously. Photometry to gauge brightness, morphology to classify shapes, redshift calculations to determine distances, physical parameters to estimate masses and ages. The catalogue represents one of the highest quality datasets in astronomy. Scientists released everything to the public. The images, the measurements, the catalogue, an interactive viewer where anyone can search for specific objects or explore random patches of deep space. This democratization of data means researchers worldwide can mine the information for discoveries. Before Webb launched, astronomers predicted they would find approximately 10 times fewer galaxies at extreme distances. They estimated galaxies forming within the first 500 million years would be incredibly rare, perhaps a few dozen in a survey this size. The actual count exceeded predictions by a factor of 10. Hundreds of extremely distant galaxies crowded into a cosmic era that should have been nearly empty. Something about early galaxy formation is fundamentally wrong in our models. The Big Bang happened 13.8 billion years ago, confirmed by multiple independent measurements. Afterward, the universe was smooth, nearly uniform. Tiny density fluctuations existed, but matter was spread almost evenly throughout space. Gravity amplifies these fluctuations over time, pulling matter into clumps that eventually become stars and galaxies. This process should be slow, predictable, gradual. Current models estimate how quickly the first structures could form. Gas needs time to cool enough for gravity to compress it. Dark matter halos need to accumulate sufficient mass to attract ordinary matter. Stars need to ignite and produce the heavy elements that seed future star formation. Each step takes millions of years. The math adds up to a clear prediction about how many galaxies should exist at any given cosmic age. Webb found 10 times more galaxies in the early universe than those predictions allowed in times. Researchers checked the instruments, verified the measurements, examined the data for errors. Everything confirmed the same impossible result. Within the first 500 million years after the Big Bang, the cosmos was teeming with galaxies, bright ones, massive ones, galaxies containing billions of stellar masses worth of material. The universe was producing too much light, too early. It had only 400 million years to form structures containing 1 billion times the mass of our Sun. We don't know how to make that happen, not with current physics, not with current understanding of how matter behaves. One explanation suggests that stars formed more efficiently in the early universe. Perhaps gas collapsed faster because the cosmos was denser. Perhaps gravitational collapse worked differently when space was more compressed. Perhaps environmental conditions allowed star formation to proceed at rates impossible in the modern universe. But this is speculation, not confirmed theory. The observations are real. The explanations remain uncertain. Another possibility involves dark matter. Different models of dark matter predict different abundances of dark matter halos in the early universe. If dark matter behaves differently than the standard model assumes, it could create conditions that accelerate galaxy formation. Measurements from Webb might help distinguish between competing dark matter theories. What troubles astronomers most is the consistency of the surprise. It's not one anomalous galaxy, it's hundreds across multiple surveys, in different regions of sky, using different instruments. Every deep field Webb examines reveals the same pattern: far more galaxies than should exist. The implications reach beyond simple number counts. If galaxies formed this abundantly, they must have influenced their surroundings earlier than expected. They would have started reionizing the universe sooner. They would have enriched space with heavy elements faster. They would have seeded the formation of larger structures earlier. The entire timeline of cosmic evolution might need revision. Every textbook chapter on the early universe might be incomplete. And some of those early galaxies are so massive they border on impossible. Astronomers discovered galaxies in the infant universe that weigh 100 times more than theory permits. These objects appeared so impossible that researchers initially called them universe breakers because their existence seemed to violate the laws of cosmology. The problem comes down to time. Building a massive galaxy requires accumulating enormous amounts of matter. Dark matter must collapse into a halo first, then ordinary matter falls into that halo, then gas cools and fragments, then stars form, then those stars live out their lives and die. Then the heavy elements they produce seed the next generation of stars. This cycle repeats over and over as the galaxy grows. Each step has a minimum duration determined by physics. You can't compress gas faster than the speed of sound without creating shock waves that heat it back up. You can't form stars instantly. You can't skip the waiting period while stellar evolution proceeds. The standard model of cosmology calculates exactly how massive a galaxy can become at any given age. Some early galaxies exceeded those limits by factors of 10 to 100. They appeared to contain more stars than should be possible given the time available. Their brightness suggested stellar populations too large for the cosmic era in which they formed. Scientists scrambled to explain this. Perhaps the galaxies weren't as massive as they appeared. Perhaps bright active galactic nuclei made them look bigger. Perhaps supermassive black holes at their centers contributed significant light, making the galaxy seem more luminous than the stars alone would produce. Recent analysis suggests this explanation is partially correct, though not completely. Some of the universe breakers do harbor extremely bright black holes that inflated their apparent mass. When astronomers account for black hole contributions and reanalyze the data, the galaxies shrink to more reasonable sizes. They're still massive for their age, but they no longer break the universe. However, even after corrections, roughly twice as many massive galaxies exist in the early universe as models predict. The discrepancy has narrowed from a factor of 100 to a factor of 2, but the problem hasn't disappeared. Something about early galaxy formation remains unexplained. One team compared Webb observations to Hubble's census of galaxies at similar distances. Hubble had been observing for decades, building a representative sample of what existed in various cosmic epochs. If the standard model was correct, Webb and Hubble should see similar distributions of galaxy masses. Any increase in Webb's counts should come from detecting fainter galaxies Hubble missed. Instead, Webb found far more bright, massive galaxies than Hubble's data suggested should exist. This inconsistency points to either environmental differences in the early universe or gaps in our understanding of how efficiently matter converts into stars. The research continues. Each new observation refines the puzzle. Each measurement narrows the range of possible explanations. What remains certain is that massive structures appeared earlier than expected, and at the centers of some of these galaxies lurk monsters even more perplexing. A supermassive black hole sits at the heart of galaxy GN11, one of the most distant galaxies ever observed. This black hole existed when the universe was only 430 million years old. Its mass equals millions, or possibly billions, of times the mass of our Sun. That should be impossible. Black holes form when massive stars collapse at the end of their lives. A star needs to be at least 20 times more massive than our own to create a black hole when it dies. The resulting black hole typically weighs 10 to 100 times what our Sun weighs. From there, it can grow by consuming gas, dust, and other stars. But this process takes time billions of years to reach supermassive status through gradual accumulation. 430 million years isn't enough time. Even if a black hole formed immediately after the Big Bang and consumed material continuously at the maximum possible rate, it couldn't grow to billions of solar masses by this early date. The physics of matter falling into black holes imposes strict limits on growth speed. Yet, there it was. Webb detected extremely dense gas surrounding the black hole, a signature of rapid accretion. The black hole was actively feeding, pulling matter inward at tremendous rates. Spectral analysis revealed patterns that only appear near supermassive black holes consuming gas. This galaxy isn't unique. Webb has discovered multiple supermassive black holes in the early universe. Some appear even more massive than expected for their cosmic age. Each discovery deepens the mystery of how these objects grew so large so quickly. Several theories attempt to explain this. One possibility involves dark stars, theoretical objects powered by dark matter annihilation rather than nuclear fusion. These stars could grow to millions of times the mass of our Sun before collapsing directly into massive black holes, providing a head start on growth. Another theory suggests that in the dense early universe, gas clouds could collapse directly into massive black holes without forming stars first. If conditions were right, a cloud containing 100 solar masses might compress straight into a black hole of equivalent mass. This has never been observed, but mathematical models show it's theoretically possible. A third explanation involves collisions. If smaller black holes merged frequently in the crowded early universe, they could build up mass faster than accretion alone allows. Gravitational wave detectors have confirmed that black hole mergers occur. Perhaps they happened far more often in the past. What makes these black holes especially important is their role in galaxy evolution. Black holes don't just sit passively at galactic centers, they blast out enormous amounts of energy as matter spirals inward. This radiation heats surrounding gas and can either trigger star formation or shut it down completely. Supermassive black holes help regulate how galaxies grow. Finding them so early means they influenced cosmic evolution from nearly the beginning. Their presence could explain some of the unexpected galaxy properties Webb keeps discovering. But before these black holes existed, something even stranger might have burned in the primordial darkness. Scientists detected something peculiar in the spectrum of galaxy GS 3073. The light contained an extreme imbalance of nitrogen compared to oxygen. The ratio measured 0.46, which is bizarre for any normal stellar population. Stars don't naturally produce that chemical signature. Stellar explosions don't create it either. But theoretical models predicted exactly this signature from a type of star never observed. Primordial monster stars, thousands of times more massive than our own. These theoretical giants would have formed in the very early universe from clouds of pure hydrogen and helium. No heavy elements existed yet to contaminate the gas. The first generation of stars, called Population 3, consisted entirely of the lightest atoms. Without heavy elements to help cool the gas, these clouds collapsed into much more massive stars than form today. A monster star might weigh 0 to 10, 0 times what our Sun weighs. It would burn incredibly hot. Its core would fuse helium into carbon at ferocious rates. The carbon would then capture additional helium nuclei through a process called the carbon-nitrogen-oxygen cycle, producing vast quantities of nitrogen. These stars would burn brilliantly for perhaps only a few million years before exhausting their fuel. When they died, they wouldn't explode like normal supernovae. They would collapse directly into massive black holes. but during their brief lives they would spew nitrogen-rich material into space through powerful stellar winds. That material is what Webb detected in GS 3073, the chemical fingerprint of monster stars that lived and died billions of years ago. The nitrogen they produced remained in the galaxy, mixed with later generations of normal stars, creating the unusual spectrum astronomers observed. This discovery provides the first clear evidence that population 3 monster stars actually existed. For decades they remained purely theoretical. Mathematical models showed they should form, but nobody had ever detected their chemical signatures in real galaxies. Webb changed that. The implications reach far beyond confirming a prediction. Monster stars help solve the supermassive black hole problem. If stars this massive collapsed into black holes weighing thousands or tens of thousands of solar masses, those black holes would have a huge head start on growth. They could reach supermassive status much faster than black holes formed from normal stars. Monster stars also contributed to reionization, the period when the first sources of light began ionizing the hydrogen gas that filled space. Their intense ultraviolet radiation would have stripped electrons from atoms across vast regions, making the universe transparent to light. This process transformed the cosmos from an opaque fog into the clear medium we observe today. Additionally, these stars produced the first heavy elements. Every atom of carbon, oxygen, and nitrogen in the early universe came from stellar interiors. Monster stars forged these elements faster and in greater quantities than normal stars could. They seeded the formation of subsequent star generations that could form planets and eventually life. The universe's largest stars burned at the beginning, not now. They were brief but essential architects of everything that followed. Yet even these giants were just individual objects. The universe's true scale reveals itself in its largest structures. The universe isn't distributed evenly. Galaxies cluster along threads of dark matter that stretch tens of millions to hundreds of millions of light-years across space. These filaments connect at massive intersections where thousands of galaxies accumulate. Between the threads lie voids, vast empty regions where almost nothing exists. This pattern is called the cosmic web. It's confirmed as the largest structure in the universe. Every major concentration of matter connects to it. Every galaxy lives somewhere on its threads. The web pervades the entire observable cosmos, integrating all gravitationally bound structures into one interconnected network. The web formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average had slightly more gravity. They pulled in more matter that increased their gravity further. The process amplified over billions of years, creating denser and denser regions connected by streams of infalling material. Think of it like water flowing downhill into valleys. The valleys represent regions of higher dark matter density. The streams represent filaments where matter flows from one concentration to another. Over cosmic time, these streams become highways of galaxies traveling along gravitational corridors. Dark matter provides the scaffolding. It comprises 85% of all matter in the universe, confirmed by gravitational effects on visible matter. Dark matter doesn't emit light or interact with electromagnetic radiation. We detect it only through its gravity. Where dark matter concentrates, normal matter follows. Scientists map the cosmic web by surveying millions of galaxies and measuring their positions in three-dimensional space. Patterns emerged. Galaxies line up along specific directions. They cluster at nodes where multiple filaments intersect. They avoid regions between filaments. The distribution reveals the underlying dark matter structure. The local group, which includes our galaxy and Andromeda, sits on a filament connecting the Fornax cluster to the Virgo cluster. This filament stretches approximately 110 million light-years across. Light from some parts of our local structure left when dinosaurs walked on Earth. The largest concentrations occur where filaments meet. These intersections become galaxy clusters, the most massive gravitationally bound objects in existence. A typical cluster might contain 100 to 1, 0 galaxies with a total mass of 100 billion stellar masses. They represent the high-density nodes of the cosmic web. Material flows along filaments toward these clusters. Galaxies that started out isolated drift along the threads and eventually join cluster populations. As they travel, they interact with other galaxies. Collisions occur, mergers happen, gas gets stripped away by the hot plasma filling space between galaxies. These environmental effects transform spiral galaxies into elliptical ones. Recent observations detected dark matter directly on filaments for the first time. Using gravitational lensing, scientists observed how light from distant objects bent around invisible mass concentrations along cosmic web threads. The measurements confirmed that dark matter really does line the filaments, not just concentrate at nodes. For the first time, scientists detected dark matter hanging from the cosmic web's terminal segments, the thin threads connecting clusters to individual galaxies. This confirmed theoretical predictions about how the largest structure organizes space. But Webb revealed something even more extreme, specific concentrations that challenge the limits of what the Webb can build. Astronomers using Webb data discovered a massive chain of at least 20 closely packed galaxies. They call it the cosmic vine. It swoops through space in a bow shape, stretching more than 13 million light-years long and approximately 650 light-years wide. For comparison, our entire galaxy measures only 100 light-years across. All 20 galaxies showed a redshift of roughly 3.44, meaning their light traveled between 11 and 12 billion years to reach us. They existed when the universe was only a few billion years old. The vine formed during an era when such large structures shouldn't have had time to assemble. What makes the cosmic vine remarkable is its size compared to other galaxy groups at similar distances. It's significantly larger than anything else discovered at this cosmic epoch. The structure appears to be in the process of becoming a galaxy cluster, one of the universe's most massive formations. Current mass estimates place the vine at approximately 260 billion stellar masses. That's already enormous, but it's still growing. Galaxies continue to drift along the filament, drawn by the combined gravity of the structure. Eventually, over the next several billion years, these galaxies will merge into a unified cluster. What puzzles researchers is the state of the two largest galaxies in the vine. When scientists analyzed the wavelengths of light these galaxies emitted, they found that star formation had almost completely stopped. The galaxies are classified as quiescent, meaning they're no longer actively producing new stars. This is unusual for the early universe. Most galaxies at this distance are still forming stars vigorously. Finding large galaxies that have already used up their gas reserves suggests something dramatic occurred. One possibility is that these galaxies resulted from recent mergers. When galaxies collide, they can trigger massive bursts of star formation that consume available gas in a relatively short period. The collision would heat the gas to extremely high temperatures. Hot gas doesn't collapse easily to form stars. It can also be expelled from the galaxy entirely by the energy released during the merger. This would leave behind a galaxy full of existing stars, but depleted of the raw material needed to build new ones. Another explanation involves the environment. Galaxies in dense structures experience different conditions than isolated galaxies. They pass through hot plasma filling the space between galaxies. This plasma can strip away their gas through a process called ram pressure stripping. Imagine sticking your hand out of a car window at highway speeds. The air resistance pushes your hand backward. Gas in galaxies experiences similar forces when moving through the hot medium between galaxies. The cosmic vine represents just one example of unexpected large-scale structure in the early universe. Webb keeps finding massive concentrations that formed faster than models predict. Each discovery adds evidence that something about early structure formation proceeds more efficiently than standard theory allows. These enormous structures don't exist in isolation. They're part of a much larger population of galaxy groups that Webb has catalogued across cosmic time. A team of astronomers compiled the largest and deepest sample of galaxy groups ever observed. They detected 678 galaxy groups and protoclusters spanning from 12 billion years ago to approximately 1 billion years ago. This catalogue maps cosmic family trees from near the beginning. Each galaxy group represents a collection of galaxies held together by gravity. They're smaller than massive clusters but larger than individual galaxies. Think of them as neighborhoods in the cosmic web, distinct communities connected by the larger structure but maintaining their own local gravitational identity. What makes this catalogue revolutionary is its depth. Previous surveys could only glimpse parts of this evolutionary sequence. They might catch groups at one cosmic epoch or another, but they couldn't trace continuous development across billions of years. Webb changed that. Its infrared sensitivity allows detection of galaxies 1 billion times fainter than what human eyes can see. The catalogue reveals how galaxy groups evolve over time. In the early universe, groups appear chaotic. Galaxies show irregular shapes. Star formation proceeds vigorously. The structures are loose, still assembling, not yet settled into stable configurations. As time progresses, the groups become more organized. Galaxies develop symmetrical shapes like spirals and ellipses. Star formation slows down, a process called quenching. The groups grow more compact as gravity pulls members closer together. Eventually, many groups merge into larger clusters. This evolution reflects broader processes shaping cosmic structure. Dark matter halos accumulate over time. Small halos merge into larger ones. Gas heats up as it falls into these halos. Supermassive black holes at galactic centers blast energy into surrounding space. All these effects combine to transform the properties of galaxies and the groups they inhabit. Scientists can now track individual galaxy populations through multiple evolutionary stages. They identify galaxies at one distance, then look for similar galaxies at other distances to see how that population changed. This creates a narrative of cosmic history, showing how different types of galaxies emerged and evolved. The catalogue also reveals environmental effects. Galaxies in dense groups behave differently than isolated field galaxies. Group members experience more frequent interactions. They collide more often. Their gas gets heated by the hot plasma filling space between them. These environmental factors accelerate evolution, transforming active star-forming galaxies into quiescent ones faster than would happen in isolation. One particularly striking finding involves the transition from chaotic to organized. The shift occurs fairly rapidly in cosmic terms over just a few billion years. Early groups show high star formation rates and irregular morphologies. Later groups show low star formation and regular shapes. The transformation coincides with the era when dark matter accumulation shifted from rapid growth to slower consolidation. This catalogue provides observational evidence for theories about how structure forms in the universe. It confirms predictions about halo assembly. It validates models of environmental quenching. It demonstrates how the cosmic web organizes matter on the largest scales. Yet, even with nearly 1,700 groups catalogued, vast regions of space contain nothing at all. Between the filaments of the cosmic web stretch enormous empty regions called voids. These spaces contain almost no galaxies, almost no stars, almost no matter of any kind. They extend for hundreds of millions of light years in every direction, representing the largest continuous volumes of emptiness in the universe. The voids aren't completely empty. A few small galaxies drift through them, isolated and alone. Sparse filaments of dark matter thread through the edges. But compared to the dense regions where galaxy clusters form, voids contain less than 10% of the average matter density of space. Imagine standing in the middle of a void. Look in any direction and you would see darkness extending for tens of millions of light years before encountering the nearest galaxy. The void would appear as a cosmic desert, an immense region where structure formation failed to occur. Voids formed through a process opposite to how clusters form. Regions that started slightly less dense than average had slightly less gravity. Matter flowed out of these regions toward denser areas. This decreased their density further. The process continued for billions of years, creating vast underdense regions while concentrating matter along the boundaries. These boundaries are where filaments exist. Matter drains from voids and accumulates on the walls, separating them. Over time, voids grow larger as more material evacuates toward the edges. The cosmic web evolves by expanding voids and compressing filaments, creating an increasingly structured pattern. The largest known void stretches approximately 1 billion light-years across. That's roughly 1% of the observable universe's diameter. Light takes 1 billion years to cross it. If you started at one edge and traveled at the speed of light, you would spend 1 billion years crossing nothing but empty space before reaching the other side. Scientists study voids because they provide clean laboratories for understanding cosmic expansion and dark energy. In dense regions, local gravitational effects complicate measurements. Galaxies move under the combined influence of large-scale expansion and local attraction. In voids, local effects are minimal. Galaxies move primarily under the influence of cosmic expansion, making them ideal tracers of how fast the universe is expanding. Void statistics also test cosmological models. The number, size, and distribution of voids depends sensitively on dark matter properties and the initial conditions after the Big Bang. Observing more or fewer voids than predicted would indicate problems with standard theory. So far, void counts match predictions, providing evidence that current models capture the broad outlines of structure formation correctly. What makes voids slightly unsettling is their extremity. The universe could have distributed matter more evenly. Instead, it created these vast empty regions and concentrated almost everything into thin threads and dense nodes. The contrast emphasizes how gravity organizes space, pulling matter together and leaving enormous gaps. Within those gaps, any civilization that arose would see a very different night sky than we do. They would observe far fewer galaxies. Their view of the cosmos would be limited. They might conclude that the universe contains less than it actually does. Meanwhile, the light traveling through both voids and filaments undergoes a transformation that reveals just how far it has come. Every wavelength of light the most distant galaxies emit gets stretched by the expansion of space. Ultraviolet light becomes visible light. Visible light becomes infrared. Infrared stretches into far infrared and beyond. By the time these ancient photons reach our telescopes, their wavelengths have expanded by a factor of 14 to 16 times their original length. This effect is called redshift. The term comes from the fact that stretching wavelengths moves light toward the red end of the spectrum. Blue light shifts to red shifts to infrared. The farther a galaxy sits, the more its light has stretched during transit, and the higher its redshift value. Scientists measure redshift using spectroscopy. Specific atoms emit light at precise wavelengths. Hydrogen produces a characteristic line at 92 nanometers in the ultraviolet. When astronomers observe this line shifted to 1/380 nm in the infrared, they know the light has been stretched by a factor of 15. This indicates a redshift value around 14. That factor of 15 tells us how much the universe has expanded since the light was emitted. When a galaxy with redshift 14 emitted its light, the universe was 15 times smaller than it is today. All distances were 15 times shorter. All wavelengths were 15 times compressed. Space itself has grown 15-fold since those photons began their journey. Here's where this becomes visually dramatic. The galaxy emitted ultraviolet and blue light from hot young stars. We see none of that in its original form. Every ultraviolet photon has shifted into near-infrared wavelengths between 1 and 3 microns. Every visible photon has stretched to mid-infrared between 3 and 10 microns. The entire spectrum has slid beyond what human eyes can detect. This is why Webb uses infrared detectors. The telescope was specifically designed to observe light from the most distant galaxies, knowing that light would arrive in infrared wavelengths. Previous telescopes like Hubble operated primarily in visible and ultraviolet light. They could detect some infrared, but not at the sensitivity needed to see faint, high redshift galaxies. Webb's instruments cover wavelengths from 0.6 microns to 28 microns. This range captures redshifted light from galaxies at virtually any distance in the observable universe. The near-infrared camera operates from 0.6 to 5 microns. The mid-infrared instrument covers 5 to 28 microns. Together, They see light that has been stretched by factors ranging from 2 to more than 20. The redshift also affects brightness. Stretching wavelength spreads the energy across a broader spectrum, making objects appear dimmer. Additionally, the expansion of space decreases the rate at which photons arrive. Both effects combine to make high redshift galaxies incredibly faint, despite being intrinsically luminous. Webb overcame this through sheer sensitivity. Its large mirror collects more light than any previous space telescope. Its instruments detect incredibly faint signals. Its position at the second Lagrange point, 1 million miles from Earth, eliminates interference from our planet's heat and light. All these factors allow it to capture photons that have been traveling for 13 billion years. But even as Webb confirms the extreme stretching of light, it has revealed a deeper problem with how we understand expansion itself. The universe is expanding. This is confirmed fact. But when scientists measure how fast it's expanding, they get different answers depending on which method they use. This discrepancy is called the Hubble tension, and it represents one of the most significant mysteries in modern cosmology. One method looks at the early universe. Scientists measure the cosmic microwave background, the faint radiation left over from the Big Bang. This radiation shows a pattern of hot and cold spots that reveals the universe's properties 13.8 billion years ago. From that pattern, they can calculate how fast the universe should be expanding today. The answer comes out to approximately 67 kilometers per megaparsec. The other method looks at the nearby universe. Astronomers measure distances to galaxies using objects called Cepheid variable stars and Type 1a supernovae. Both serve as standard candles whose intrinsic brightness is known. By comparing how bright they appear to how bright they actually are, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate. This method yields approximately 73 kilometers per megaparsec. The gap might seem small, just 6 kilometers per megaparsec, but this difference is statistically significant. Both measurements have been verified repeatedly using independent data sets. The cosmic microwave background measurements come from multiple satellites and ground-based telescopes. The nearby universe measurements come from Hubble observations spanning decades. Webb has now confirmed Hubble's measurements using the largest sample of Webb data collected over its first 2 years in space. The team used 3 different methods to measure distances to galaxies that hosted supernovae. All 3 methods agreed with each other and with Hubble's earlier results. Webb's measurements ruled out the possibility that Hubble made a systematic error, so the tension remains. The early universe predicts one expansion rate, the late universe measures another. These cannot both be correct if our understanding of how the universe evolves is accurate. Several possible explanations exist. Maybe dark energy behaves differently than current models assume. Instead of remaining constant over time, perhaps its strength has changed as the universe aged. This would cause the expansion rate to differ between early and late epochs. Maybe there's some unknown physics affecting how light travels through space. Perhaps interactions with dark matter or other fields modify photon energies in ways we haven't accounted for. This could bias measurements in one direction or another. Maybe our measurements contain unrecognized errors. Perhaps some subtle systematic effect contaminates one or both methods. Scientists continuously search for such errors, but none has been found that could explain the entire discrepancy. The most intriguing possibility is that the tension reveals genuinely new physics. Perhaps the universe evolved in ways not captured by the standard model of cosmology. Perhaps additional forces or particles exist that influence cosmic expansion. Finding such new physics would revolutionize our understanding of reality at the most fundamental level. What makes this especially troubling is that the Hubble constant isn't just an academic number. It reveals how the universe has evolved over its entire history. It determines the universe's age, size, and ultimate fate. Getting it wrong means misunderstanding the cosmos at the largest scales. And speaking of large scales, scientists just confirmed the existence of something that had only been theorized for decades. Dark matter makes up 85% of all matter in the universe. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation at all. We know it exists only because of its gravitational effects on visible matter. Galaxies rotate too fast to be held together by the gravity of their stars alone. Galaxy clusters move in ways that require far more mass than we can see. The cosmic web wouldn't exist without dark matter providing the scaffolding. For decades, scientists theorized that dark matter should line the filaments connecting galaxy clusters. Mathematical models showed it clearly. Simulations demonstrated how dark matter would flow along these threads, creating channels where ordinary matter would follow. But nobody had directly observed dark matter on the filaments themselves. Until now, researchers from Yonsei University in Seoul used the Subaru telescope in Hawaii to study the Coma cluster, a collection of over 10 galaxies located 321 million light-years away. They employed gravitational lensing, an effect where massive objects bend light passing nearby. When light from distant galaxies travels past a concentration of dark matter, the dark matter's gravity curves space, causing the light to follow a curved path. This creates distortions in the images of background galaxies. Their shapes appear stretched or warped. By carefully measuring these distortions, astronomers can map where dark matter concentrations exist. The team detected dark matter along the terminal segments of cosmic web filaments dangling from the Coma cluster. These terminal segments are the thin threads connecting the main filament to individual galaxies. Previous observations had seen dark matter in the main filaments and at the nodes where filaments intersect. This marked the first detection on the smallest threads of the web. This discovery confirms theoretical predictions about how the cosmic web organizes space. Dark matter doesn't just concentrate at nodes, it genuinely pervades the entire network, creating a continuous structure spanning the universe. Galaxies don't drift through empty space. They slide along dark matter highways that guide their motion. The Coma cluster itself sits on what's called the Great Wall, one of the largest structures ever discovered. The Great Wall was actually the first super-large structure identified in the universe. It's a massive sheet of galaxies stretching across hundreds of millions of light-years. The Coma cluster represents one of the densest regions where multiple filaments converge. What makes this observation technically impressive is the difficulty of gravitational lensing measurements. The distortions are subtle. Background galaxies appear only slightly stretched. Detecting this requires extremely precise measurements of galaxy shapes, correlating those shapes across large areas of sky, and carefully removing all other sources of distortion, like atmospheric effects or telescope optics. The Subaru telescope's 8.2-meter mirror and advanced instruments made these measurements possible. The team analyzed hundreds of background galaxies, looking for systematic patterns in how their shapes were warped. The pattern revealed the gravitational influence of dark matter threading through space. This finding matters because it provides direct observational evidence for the cosmic web's most basic prediction. If dark matter exists and organizes on large scales, it must line the filaments. Now, we've seen it doing exactly that. The universe's largest structure has revealed its invisible skeleton, and that structure might be far more populated than anyone imagined. For years, astronomers estimated the universe contains approximately 200 billion galaxies. This number came from Hubble surveys that counted galaxies in small patches of sky, then extrapolated to the entire observable sphere. The calculation seemed solid. Multiple independent surveys agreed. Webb has forced a revision. The galaxy density in Webb's deep field significantly exceeds what Hubble surveys suggested. If these deep field observations are representative of the universe as a whole, the total number of galaxies could be trillions rather than hundreds of billions. Think about what this means. Every estimate of cosmic structure, every calculation about total stellar mass, every prediction about how many stars and planets exist, all of these depend on knowing how many galaxies there are. If the true count is 10 times higher than previous estimates, everything scales up accordingly. The implication for planets is staggering. Our galaxy alone contains approximately 200 billion stars. If each star has an average of one planet, that's 200 billion planets just in the Milky Way. Multiply by 200 billion galaxies, and you get 40 quintillion planets in the observable universe. But if there are actually trillions of galaxies, the number jumps to 400 quintillion planets, or Moria 4, with 21 zeros after it. The scale becomes almost incomprehensible. For every grain of sand on every beach on Earth, there might be 100 planets out there in the cosmos. The increase in galaxy counts comes from Webb's ability to see fainter objects than Hubble could detect. Many galaxies that appeared as faint smudges or weren't visible at all in Hubble images show up clearly in Webb's infrared observations. Additionally, Webb sees galaxies hidden behind cosmic dust that blocked visible light but allows infrared through. What remains uncertain is whether Webb's deep field observations truly represent average galaxy density. The telescope has observed relatively small patches of sky in extreme detail. Perhaps those patches happen to be denser than typical. Perhaps the galaxy distribution varies significantly across different regions of the observable universe. Scientists are working to answer this by conducting surveys of larger sky areas at somewhat lower depth. If those surveys show similar galaxy densities to the ultra-deep fields, it confirms the higher total count. If the density decreases in wider surveys, it suggests the deep fields represent the true average. Early results favor the higher density. Multiple deep field observations in different directions show consistently high galaxy counts. This suggests the abundance is real, not a statistical fluke. The philosophical implications are profound. If trillions of galaxies exist, each containing billions or trillions of stars, each potentially hosting planets, the probability of other life existing somewhere becomes nearly certain. The cosmos is so vast, with so many opportunities for chemistry and evolution, that Earth being unique seems implausible. Yet, all these trillions of galaxies exist in the observable universe alone. The total universe extends far beyond what we can see. Some models suggest it might be infinite. If so, the number of galaxies isn't trillions. It's literally infinite. An endless expanse of stars and planets and possibilities. Even in the most distant galaxies Webb has observed, something unexpected is happening with star formation. Star formation has a speed limit. Gas must cool before gravity can compress it into stars. Hot gas generates pressure that resists gravitational collapse. Only when the gas cools sufficiently does gravity win, allowing the cloud to fragment and form stellar nurseries. This cooling process takes time. In the modern universe, star formation proceeds relatively slowly. A typical molecular cloud might produce a few solar masses worth of new stars per year. This rate reflects the balance between cooling and heating, between gravity and pressure. The process is inefficient. Most of the gas doesn't become stars. It gets blown away by stellar winds or heated by radiation. The early universe appears to have operated differently. Galaxies just a few 100 million years old show stellar populations suggesting they formed stars at rates 10 to 100 times faster than modern galaxies of equivalent mass. They converted their gas into stars with shocking efficiency. The evidence comes from measuring galaxy brightness and mass. A galaxy's brightness depends on how many stars it contains and how hot those stars burn. Young, massive stars burn extremely bright. By analyzing the spectrum of light a galaxy emits, scientists can estimate how quickly it's producing new stars. Comparing that rate to the galaxy's total mass reveals how efficiently it converts available material. Early galaxies show mass-to-light ratios, indicating they turned gas into stars much faster than current models predict. One explanation suggests the early universe was denser, making gravitational collapse more effective. When matter is compressed into a smaller volume, clouds collide more frequently. Collisions trigger star formation. Higher collision rates mean more stars. Another possibility involves gas composition. The first generations of stars formed from pure hydrogen and helium. Modern stars form from gas enriched with heavy elements produced by previous stellar generations. Heavy elements help gas cool more efficiently through various atomic processes. Paradoxically, this might make modern star formation slower. Pure hydrogen gas might collapse more rapidly under the right conditions because it has fewer cooling channels that could complicate the collapse process. Environmental factors could also play a role. Early galaxies experienced more frequent mergers because the universe was smaller and galaxies were closer together. Mergers funnel gas toward galactic centers, where it accumulates in dense concentrations. These dense regions can form stars at tremendous rates, sometimes producing thousands of solar masses per year in brief periods called starburst events. However, these explanations remain partly speculative. Nobody has definitively proven why early star formation proceeded so rapidly. Observations confirm it happened. Theory struggles to fully explain how. What makes this especially puzzling is that rapid star formation should deplete available gas quickly. If a galaxy forms stars at 100 times the normal rate, it should exhaust its fuel in 1/100th the usual time. Yet, many early galaxies show large stellar populations that required sustained star formation over millions or tens of millions of years. Where did all that gas come from? How did it remain available instead of being consumed immediately? One possibility involves cold gas streams. Simulations show that gas can flow directly from intergalactic space into galaxies along cosmic web filaments. This continuous supply could fuel high star formation rates without requiring enormous initial gas reservoirs. What becomes clear is that the early universe was not simply a younger version of today's cosmos. It operated under different conditions that produced different outcomes. The most massive structures gravity can hold together are galaxy clusters. These are the nodes where cosmic web filaments intersect regions so dense with matter that hundreds or thousands of galaxies congregate in a volume spanning just a few million light-years. A typical massive cluster contains approximately 100 trillion times the mass of our Sun. That number is almost impossible to comprehend. 100 trillion. Written out, it's 1 followed by 14 zeros. Most of that mass isn't even in galaxies. It's spread through space as hot plasma and invisible dark matter. The Coma cluster mentioned earlier contains over 10 galaxies. The entire structure weighs roughly 10 quadrillion solar masses. Light takes millions of years to cross from one side to the other. If you could somehow stand in the middle of this cluster, you would see galaxies in every direction, filling the sky with distant spirals and ellipticals. These clusters emit tremendous amounts of X-ray radiation. The space between galaxies isn't empty. It's filled with plasma, heated to tens of millions of degrees. This plasma formed when galaxies fell into the cluster's gravitational well. As they plummeted inward, friction with existing gas heated both to extreme temperatures. The hot gas now radiates energy across the electromagnetic spectrum. Galaxy clusters also serve as gravitational lenses. Their enormous mass warps space-time so severely that light from background galaxies bends around them. This creates multiple images of the same distant galaxy stretched into arcs and rings. Astronomers use these distortions to measure the cluster's total mass, including dark matter that emits no light. What scientists discovered is that dark matter comprises approximately 85% of a cluster's total mass. The galaxies themselves account for only a few percent. The hot plasma makes up another 10 to 15%. The rest is dark matter detected only through its gravitational effects. These measurements confirmed that dark matter exists and dominates cosmic structure. Without dark matter, clusters would fly apart. The galaxies move too fast for the gravity of visible matter alone to hold them together. Dark matter provides the additional gravity needed to keep everything bound. Clusters also mark the end of structure formation at the largest scales. Superclusters exist, which are collections of multiple clusters connected by filaments. But superclusters aren't gravitationally bound. They're simply regions where clusters happen to be relatively close. Cosmic expansion will eventually pull superclusters apart. Clusters represent the largest objects that will remain intact as the universe continues expanding. As time progresses, clusters will absorb more galaxies from surrounding filaments. They'll grow more massive. Their gravitational pull will strengthen. Eventually, billions of years from now, the galaxies within clusters will merge into single, enormous elliptical galaxies. The cluster will become a swarm of stars, instead of a collection of distinct galaxies. But clusters aren't just being pulled together by gravity. They're also being pushed apart by something far more mysterious and far more powerful. 68% of everything that exists is dark energy, not dark matter, not ordinary matter, not radiation dark energy. A mysterious force that pushes space apart, accelerating cosmic expansion. Scientists discovered dark energy in 1998 by observing distant supernovae. Type 1a supernovae explode with consistent brightness, making them excellent distance markers. When astronomers measured how fast these supernovae were receding, they expected to find that cosmic expansion was slowing down. Gravity should gradually break the expansion over billions of years. Instead, they found expansion accelerating. Distant supernovae were farther away than they should be. If expansion had remained constant or decreased, something was pushing space apart faster and faster. That something is dark energy. Dark energy has a bizarre property. Its density remains constant as the universe expands. Normal matter gets diluted when space grows larger. If you have 1 particle per cubic meter, doubling the volume gives you 1 particle per 2 cubic meters. The density decreases. Dark energy doesn't work this way. When space expands, dark energy's density stays the same. More space means more total dark energy. Think about what this implies. As the universe grows, matter and radiation become less influential because they spread out. Dark energy becomes more influential because its total amount increases while its density stays constant. Early in cosmic history, matter dominated. Gravity was the primary force shaping structure. About 5 billion years ago, dark energy took over. Now it dominates the universe's evolution. The observable universe spans 93 billion light-years because dark energy has been pushing space apart for billions of years. Without dark energy, the universe would be smaller. Expansion would have proceeded more slowly. The farthest galaxies we can see would be closer. The cosmic horizon would be nearer. Dark energy also determines the universe's future. If dark energy strength remains constant, cosmic expansion will continue accelerating forever. Galaxy clusters will remain gravitationally bound, but everything outside our local group will eventually recede beyond the cosmic horizon. Trillions of years from now, any observers in our galaxy will see only darkness beyond our immediate neighbors. The rest of the universe will have raced away faster than light can travel. If dark energy strengthens over time, the outcome becomes more extreme, an accelerating acceleration. Eventually, dark energy might grow strong enough to overcome gravity on smaller scales. It would rip apart galaxy clusters, then galaxies, then star systems, then planets, then molecules, then atoms. This scenario is called the Big Rip. It's theoretical, not confirmed, but measurements of dark energy's properties help determine if it's possible. Current measurements suggest dark energy strength has remained relatively constant over the past several billion years. The equation of state parameter, which describes how dark energy's pressure relates to its density, appears to be approximately 1. This value corresponds to a cosmological constant, Einstein's original proposal for why the universe doesn't collapse under gravity. But measuring dark energy's properties precisely is difficult. Small uncertainties in the measurements leave room for various theoretical possibilities. Scientists continue observing distant supernovae, mapping galaxy distributions, and measuring cosmic expansion to nail down exactly how dark energy behaves. What remains absolutely certain is that dark energy exists, dominates the cosmos, and controls the universe's ultimate fate. And as it pushes space apart, something strange happens to time itself. Cosmic expansion affects time. This is confirmed by Einstein's theory of relativity. As space expands, objects at different distances experience time at different rates relative to an observer. The effect is subtle but real. Consider a galaxy at the edge of the observable universe. From our perspective, that galaxy appears to be moving away at speeds approaching the speed of light. According to relativity, time slows down for objects moving at high velocities relative to an observer. This means clocks in that distant galaxy tick slower from our viewpoint. But here's where it gets strange. From the perspective of observers in that distant galaxy, their clocks tick normally, They see our galaxy moving away at near light speeds. From their viewpoint, our clocks are the ones running slow. Both perspectives are equally valid. Time dilation is relative, not absolute. This creates a peculiar situation at cosmic horizons. Galaxies currently at the edge of the observable universe are receding at the speed of light due to cosmic expansion. From our frame of reference, time in those galaxies has slowed to a near stop. We see them frozen at a particular moment in their evolution. Their light reaches us, but it's been redshifted to such extreme wavelengths that it becomes nearly impossible to detect. As cosmic expansion accelerates, more galaxies will cross this horizon. They'll recede faster than light can travel through expanding space. Once they cross that boundary, no signal they emit will ever reach us. They effectively disappear from the observable universe. From our perspective, they freeze at the moment they cross the horizon, their time appearing to stop completely. Meanwhile, objects closer to us experience less time dilation. Nearby galaxies recede slowly enough that time dilation effects are minimal. Galaxies in our local group aren't receding at all. We're all gravitationally bound together. Time passes normally for them relative to us. This means the observable universe is filled with objects at different stages of time progression from our viewpoint. The farthest galaxies appear frozen in the early universe. Intermediate distance galaxies show moderate time dilation. Nearby galaxies experience time at rates similar to ours. We're looking at a temporal gradient spanning the entire cosmic horizon. Gravitational time dilation adds another layer of complexity. Regions of stronger gravity experience slower time relative to regions of weaker gravity. Near a massive galaxy cluster, time passes slightly slower than in the voids between filaments. Near a black hole, time slows dramatically. At the event horizon of a black hole, time appears to stop completely from an external observer's perspective. All these effects combined create a universe where time is not a single universal flow, but a complex patchwork of different rates depending on location, velocity, and gravitational environment. Every point in space has its own unique experience of time's passage. For practical purposes, these differences are usually tiny. Human lifespans are too short to notice cosmic time dilation. Even over the history of Earth, the effects are negligible, but when observing across billions of light years and billions of years of cosmic history, time dilation becomes significant. Webb observes galaxies as they appeared billions of years ago, but from those galaxies' perspectives, time has continued flowing normally. They've evolved, changed, possibly merged with other galaxies, or died in collisions. We'll never see those later stages because the light showing us what happened next is still traveling through space, stretched and diluted by expansion. What we see is a universe frozen in layers of the past, each layer representing a different cosmic epoch and a different moment in time. Hubble Space Telescope launched in 1990 and revolutionized astronomy for over 3 decades. It captured stunning images of the cosmos. Its ultra-deep field showed nearly 10.0 galaxies in a patch of sky the size of a grain of sand held at arm's length. Scientists considered it the deepest view ever obtained. Then Webb pointed at the same regions where Hubble saw empty darkness between galaxies. Webb detected countless additional objects. Faint red smudges invisible to Hubble blazed clearly in Webb's infrared detectors. The darkness wasn't empty. It was filled with galaxies Hubble simply couldn't see. The difference comes down to wavelength. Hubble operates primarily in visible and ultraviolet light, with some near-infrared capability. Its instruments are optimized for wavelengths human eyes can detect. This works perfectly for nearby galaxies whose light hasn't been severely redshifted. But for the most distant galaxies, visible light has stretched into infrared wavelengths. What left those galaxies as blue and ultraviolet light arrives at our telescopes as infrared radiation. Hubble's visible light detectors couldn't capture it. The galaxies remained invisible, hidden not by dust or distance, but by the fundamental properties of cosmic expansion. Webb was designed specifically to see this invisible population. Its instruments cover infrared wavelengths from 0.6 microns all the way to 28 microns. This range captures light from galaxies at virtually any redshift. The telescope operates at temperatures near absolute zero to prevent its own heat from overwhelming the faint infrared signals it's trying to detect. The result is revolutionary. Regions Hubble imaged as black voids now show structure. Galaxies appear where nothing seemed to exist. The cosmic landscape has gained depth and detail that was literally invisible before. Cosmic dust also plays a role. Dust particles scatter and absorb visible light, but allow infrared to pass through relatively unimpeded. Star-forming regions are often shrouded in thick dust clouds. Hubble saw these regions as dark patches. Webb sees through the dust to reveal the stellar nurseries hidden inside. This effect appears throughout the universe. Dusty galaxies that appeared faint or invisible in Hubble images shine brightly in Webb observations. Scientists can now study star formation in environments that were previously opaque. They can measure how much dust exists in different galaxies and different cosmic epochs. They can determine how dust affects galaxy evolution. The comparison between Hubble and Webb images of the same objects is striking. Hubble shows a relatively sparse collection of bright galaxies against black backgrounds. Webb shows those same bright galaxies plus hundreds of fainter ones filling the spaces between. The universe appears more crowded, more active, more complex. This doesn't mean Hubble was somehow inferior. Hubble revolutionized our understanding of the cosmos. It discovered dark energy. It measured the universe's expansion rate. It determined the ages of the oldest stars. It revealed supermassive black holes at galactic centers. Its contributions are immeasurable. But Hubble looked at the universe through visible light eyes. It saw what humans would see if we could travel to deep space and look around. Webb sees infrared spectrum invisible to human vision, but critical for understanding the cosmos. Together, Hubble and Webb provide complementary views that reveal far more than either could alone. What Webb reveals in infrared shows that our visible light view of the universe is incomplete. Vast populations of objects exist that human eyes could never detect, no matter how powerful our vision became. The universe contains more than what our biology allows us to perceive, and what Webb sees suggests the early universe was far more active than anyone expected. The Standard Model of cosmology makes clear predictions about the early universe. After the Big Bang, space expanded and cooled. About 380 years later, atoms formed. Another few 100 million years passed before the first stars ignited. Those stars gathered into the first galaxies. The process was gradual, proceeding over hundreds of millions of years. Galaxies should have been rare in the first 500 million years, small, dim, simple structures containing relatively few stars. The universe simply hadn't had enough time to build anything elaborate. Webb's observations contradict this timeline. Within the first 400 million years, the cosmos was already producing enormous amounts of light. Bright galaxies blazed across space. Massive structures had assembled. The early universe appears far more luminous than models predicted. Scientists are calling this the too much light too early problem. The observations are clear. Multiple independent surveys confirm it. Different instruments verify it. The early universe was brighter than it should have been, given the time available for galaxy formation. One measurement captures this problem perfectly. Researchers calculated the total amount of light produced by all galaxies in the first billion years after the Big Bang. They compared this to theoretical predictions of how much light should exist based on standard structure formation models. The observations exceeded predictions by factors of 2 to 10, depending on the exact cosmic epoch examined. 2 to 10 times more light. That's not a subtle discrepancy, it's a fundamental challenge to our understanding of how galaxies form and evolve. Something about the early universe allowed it to produce stars and galaxies far more efficiently than the same processes work today. Several explanations have been proposed. Perhaps the initial mass function was different in the early universe. The initial mass function describes the distribution of stellar masses when stars form. Modern star formation produces mostly small stars with a few massive ones. Maybe early star formation produced more massive stars proportionally. Massive stars burn brighter than small ones, so this would increase total light output. Another possibility involves star formation efficiency. In the modern universe, only a small fraction of available gas actually becomes stars. Most gas gets heated, blown away, or remains in diffuse clouds. Perhaps in the early universe, environmental conditions allowed gas to convert into stars more efficiently. Higher efficiency means more stars per unit of gas, producing more light. Black holes might contribute as well. Active galactic nuclei, powered by supermassive black holes consuming matter, can shine brighter than entire galaxies. If black holes were more common or more active in the early universe, they could account for some of the excess light. Recent observations support this idea, showing that many early galaxies harbor extremely bright active nuclei. What makes this problem especially frustrating for theorists is that observations keep pushing the boundary earlier. First, Webb found surprisingly bright galaxies at 600 million years, then at 500 million years, then at 400 million years, then at 300 million years. Each new discovery reveals that the universe was already producing significant light even earlier than previously observed. The standard cosmological model isn't completely broken. It accurately predicts many other observables like the cosmic microwave background, the distribution of elements, and large-scale structure. But it clearly misses something important about early galaxy formation. Resolving this problem might require new physics. Perhaps dark matter behaves differently than assumed. Perhaps star formation proceeds through mechanisms we haven't discovered. Perhaps the initial conditions after the Big Bang were more complex than current models capture. What remains certain is that the universe's infancy was far more active and bright than anyone predicted, and the light we see from that era traveled across distances that reveal just how limited our view truly is. Light from the edge of the observable universe has been traveling for 13.8 billion years. During that time, cosmic expansion has carried the source of that light to a current distance of 46.5 billion light-years away. This defines the cosmic horizon. Everything within 46.5 billion light-years is observable in principle. Everything beyond that boundary remains invisible. But space doesn't stop at the observable edge. The universe extends beyond our horizon. Galaxies exist out there. Stars shine, planets orbit, black holes consume matter. All of it proceeds completely unobservable from Earth. We know this because the observable universe appears roughly the same in all directions. It shows no signs of an edge or boundary. Galaxy distributions look similar whether we examine regions to our north, south, east, or west. The cosmic microwave background has nearly identical properties across the entire sky. This uniformity suggests space continues beyond what we can see. Think about what this means. The observable universe is just one sphere in an expanse that extends indefinitely. Our sphere has a radius of 46.5 billion light-years. Somewhere 47 billion light-years away, galaxies exist that we will never see. Their light hasn't had time to reach us yet. Given enough time, we might think that light would eventually arrive, but cosmic expansion prevents this. Space is expanding faster than those distant regions can send light toward us. Imagine someone running on a treadmill toward you while the treadmill speeds up continuously. If the treadmill accelerates faster than they can run, they'll never reach you despite running in your direction. Light from distant galaxies faces the same problem. Dark energy accelerates expansion. Regions currently beyond the cosmic horizon are receding faster than the speed of light through expanding space. Their light travels toward us, but the space between us grows faster than the light can cross it. The gap widens instead of narrowing. Those regions are causally disconnected from us. No signal, no particle, no information can ever traverse the expanding space separating us. This creates strange implications. Events happening right now in those distant regions will never affect us. If a civilization exists 50 billion light-years away, we will never communicate with them. Their radio signals will never reach us. Our signals will never reach them. We exist in separate, isolated pockets of space. As time passes, the situation worsens. Cosmic expansion is accelerating. Regions currently inside our observable universe will eventually cross the horizon and disappear. Galaxies we can see today will redshift until their light becomes undetectable, then fade from view entirely as they recede beyond the boundary. Scientists calculate that in approximately 150 billion years, every galaxy outside our local gravitationally bound group will have disappeared beyond the cosmic horizon. Future observers in our galaxy will see a universe containing only the Milky Way, Andromeda, and a few dozen smaller galaxies. Everything else will have vanished into darkness. They might conclude that these few galaxies represent the entire universe, unaware of the billions of galaxies that once filled the sky. We are fortunate to live in an era when the universe reveals itself. We can see 13.8 billion years of cosmic history. We can observe the early universe, track galaxy evolution, measure cosmic expansion. Future civilizations might not have this opportunity. The accelerating expansion will erase the evidence. But even now, with all our telescopes and technology, we see only a fraction of what exists. The majority of the universe lies beyond our reach. The observable universe measures 93 billion light-years across. That number seems enormous. It contains somewhere between hundreds of billions and trillions of galaxies, countless stars, unimaginable numbers of planets. Yet this entire sphere represents only what we can observe, not the totality of what exists. The actual universe is larger, potentially much larger, possibly infinite. Current measurements suggest space is geometrically flat. This means parallel lines remain parallel forever. Triangles drawn across cosmic distances have angles that sum to 180 degrees. Euclidean geometry applies. And in flat, infinite space, the universe extends without bound in all directions. If the universe is infinite, then beyond our observable sphere lies more space containing more galaxies stretching on forever. For every galaxy we can see, infinite galaxies exist that we cannot. For every star in the observable universe, infinite stars shine beyond our horizon. The numbers become meaningless because infinity exceeds any finite count by an infinite amount. Some cosmological models suggest the universe is finite, but unbounded, similar to the surface of a sphere. You could travel in a straight line and eventually return to your starting point after circumnavigating the entire space. In such a universe, the total volume is large but finite. Estimates for finite universes often place the total diameter at hundreds of billions or even trillions of light-years, still vastly larger than what we observe. Whether finite or infinite, the universe beyond our horizon contains structures and phenomena we cannot detect. Galaxy clusters form there. Cosmic web filaments connect across distances we'll never measure. Stars explode. Black holes merge. Entire populations of objects exist in complete isolation from our observable region. This raises a profound question about scientific knowledge. We develop theories based on observations. We test those theories through experiment and measurement. Our most successful theories, like general relativity and quantum mechanics, have been verified countless times within the observable universe. But do they apply beyond our horizon? We assume physical laws are universal, but we cannot verify this assumption for regions we can never observe. Most scientists believe the universe is uniform on the largest scales. The cosmological principle states that the universe looks roughly the same everywhere when averaged over sufficiently large volumes. Our observable region appears typical, not special. If this principle holds, then regions beyond our horizon should contain similar densities of galaxies, similar structures, similar physical processes. But we cannot prove this. It's an assumption based on symmetry and simplicity, not direct observation. Perhaps regions beyond our horizon differ dramatically. Perhaps different physical constants apply there. Perhaps entirely different forms of matter and energy dominate. The multiverse hypothesis takes this idea further. Some inflationary cosmology models suggest our observable universe is one bubble in a vast foam of separate universes. Each bubble underwent its own Big Bang-like event. Each evolved independently. Different physical laws might apply in different bubbles. We exist in this particular bubble because its properties allow life to develop. Other bubbles might be sterile, lacking the right conditions for complexity to emerge. These ideas remain speculative. No observations confirm or rule out multiverse scenarios. They exist at the boundary between physics and philosophy, addressing questions that might be fundamentally unanswerable through experiment. What we know with certainty is that our observable universe does not represent all that exists. Space extends beyond what we can see. Whether that extension is finite or infinite, uniform or varying, singular or multiple remains unknown. And every location in that extended space has its own unique view of the cosmos. Stand anywhere in the universe and look around. You see a sphere of galaxies extending to your cosmic horizon. Light from those galaxies has had time to reach you since the Big Bang. Beyond that horizon, galaxies exist that you cannot observe because their light hasn't arrived yet. Now imagine standing somewhere else, galaxy 46 billion light-years from Earth. From that location, you would see a completely different observable sphere. Galaxies visible from Earth would lie beyond the horizon from that distant vantage point. Conversely, galaxies invisible to us would be clearly observable from there. Every location in space defines its own observable universe. The boundary of that observable region depends entirely on where you stand. What's inside one observer's horizon might be outside another's. No single perspective captures the totality of what exists. This creates strange situations. Consider two galaxies separated by 90 billion light-years. Neither can observe the other. They exist in causally disconnected regions of space. Yet both might be observable from Earth if they happen to lie in opposite directions from us. We could see both simultaneously, even though they cannot see each other. Or consider a galaxy exactly at our cosmic horizon. Light from this galaxy is just now reaching us after traveling for 13.8 billion years. But from that galaxy's perspective, Earth lies at their cosmic horizon. Our light is just reaching them. We see them in their distant past. They see us in our distant past. Neither observes the other as they currently are. This asymmetry of observation reveals something fundamental about the universe's structure. Space has no center, no privileged location. Every point can consider itself the center of its own observable sphere. The cosmic horizon surrounds every observer equally in all directions. If other civilizations exist in distant galaxies, they look at the universe and see patterns similar to what we observe. Galaxy distributions, cosmic web structure, the cosmic microwave background, but the specific galaxies they catalogue would be completely different from ours. Their deep field surveys would reveal objects we cannot see. Their most distant galaxy would be unknown to us. This raises interesting questions about communication. Suppose we detected a signal from a civilization 20 billion light-years away. We could potentially communicate with them despite the enormous distance. We send a message. 20 billion years later, it arrives. They respond 20 billion years after that. We receive their reply. The exchange would take 40 billion years, but it's theoretically possible. However, if a civilization exists 50 billion light-years away, communication becomes impossible. They lie beyond our cosmic horizon. Our signals cannot reach them because space expands faster than light can cross the intervening distance. We are permanently isolated from each other. This limitation applies to information of all kinds. Any event occurring beyond the cosmic horizon cannot affect us causally. No particle, no photon, no gravitational wave can traverse the expanding space to deliver information about those distant events. They might as well exist in a separate universe for all the influence they have on our region. Yet from their perspective, they face identical limitations. They cannot observe us. They cannot communicate with us. They cannot be affected by events in our region. We exist in mutually exclusive observable universes. The full universe likely contains countless observable spheres, each centered on different locations, each revealing different subsets of the total cosmic population. And each observer would be justified in asking what their observations mean for their place in existence. Webb revealed a universe far larger than previous estimates suggested, not just larger in total extent, though that too, but larger in population. More galaxies, more stars, more planets, more of everything. Trillions of galaxies instead of hundreds of billions, each containing billions or trillions of stars. each of those stars potentially hosting planets. The numbers escalate beyond comprehension. The Milky Way seemed vast when we thought it was one among 200 billion galaxies. Now it might be one among 10 trillion or more. Earth shrinks in significance with every new discovery. We orbit an average star in an average galaxy in an average region of space. Nothing about our location appears special. We're not at any center. We're not in any unusual structure. We're a typical planet around a typical star in a typical galaxy among trillions. This realization has been building for centuries. Copernicus showed that Earth orbits the Sun, not the other way around. Later, astronomers showed our star is ordinary, one among hundreds of billions. Then we learned the Milky Way is one galaxy among many. Now we learned that many means trillions, vastly more than we estimated. Each discovery displaced humanity further from any sense of cosmic importance. We are not the center of the solar system, not the center of the galaxy, not in a special galaxy, not even in an unusually large cluster. We're thoroughly average in every measurable way. Yet this displacement brings perspective. If trillions of galaxies exist, each with billions of stars and countless planets, the probability of other life existing somewhere becomes extremely high. We're probably not alone. The cosmos is too vast with too many opportunities for chemistry and evolution for Earth to be unique. This realization changes how we think about ourselves. We're one outcome among potentially billions or trillions of instances where matter organized into living systems. Our particular history, our specific biology, our individual civilizations might be unique, but life in general, intelligence in general, probably appears throughout the universe. We can never know for certain. Most of those potential civilizations lie beyond the cosmic horizon. We cannot communicate with them. We cannot observe them. They cannot observe us. We exist in isolation despite being part of a potentially populous cosmos. For the civilizations within our observable universe, detection remains incredibly difficult. Space is vast. Distances are enormous. Signals attenuate to undetectable levels across thousands or millions of light years. The universe could be teeming with civilizations, all trying to communicate, all failing to bridge the vast gulfs between stars. Webb reminds us of these gulfs. Every deep field image shows thousands of galaxies, each separated by millions or billions of light years. Each galaxy contains billions of potential homes for life. Yet the distances render them unreachable. We can see them, we can study them, we cannot visit them or communicate with anyone who might live there. What we can do is appreciate the scale, understand our place within it, recognize that we're part of something vastly larger than ourselves. The universe is 93 billion light-years across in what we can observe. Beyond that, it extends farther, possibly infinitely. We occupy one planet circling one star in one galaxy among trillions. That's not insignificant. That's our home, our origin, our context. Webb has revealed just how large that context truly is. The universe is bigger, more complex, and more magnificent than we ever imagined. And we're privileged to live in an era when we can look out and see it, understand it, and marvel at our tiny but precious place within it. At the centers of some galaxies burns a light source so intense it outshines every star in that galaxy combined. These objects are called quasars. They represent the brightest, continuously shining objects in the universe. A single quasar can emit more light than 1 trillion stars like our own. Quasars are powered by supermassive black holes consuming matter. As gas spirals inward toward the black hole, friction heats it to millions of degrees. This superheated material radiates across the entire electromagnetic spectrum. The energy output is staggering, more luminous than the combined light of hundreds of billions of stars, compressed into a region smaller than our solar system. Webb has detected quasars existing when the universe was less than 700 million years old. These ancient quasars pose the same problem as early supermassive black holes. They shouldn't exist yet. Building a black hole massive enough to power a quasar should take billions of years. Yet there they are, blazing in the infant cosmos. One quasar detected by Webb appears so bright that scientists initially questioned whether the measurement was accurate. The object shines with the luminosity of 600 trillion suns. That's more energy than our entire galaxy produces, concentrated in a space perhaps a few light months across. The light from this quasar has been traveling for over 13 billion years. During that entire journey, the quasar's radiation has been streaming through space in all directions. Only an infinitesimal fraction happens to travel in Earth's direction. The total energy this object has released into the cosmos is almost incomprehensible. Quasars also serve as cosmic flashlights. Their intense light illuminates gas clouds between them and Earth. When scientists analyze quasar spectra, they see absorption lines where intervening gas has absorbed specific wavelengths. These absorption features reveal the composition and temperature of intergalactic gas across billions of light years. This technique has mapped the cosmic web in 3 dimensions. Gas along filaments shows up as absorption in quasar light. Voids show minimal absorption. Dense regions show strong absorption. By observing many quasars in different directions, astronomers reconstruct the large-scale structure of the universe. Quasars are not permanent. They represent a phase in galaxy evolution when the central black hole feeds actively. Once the available gas is consumed or expelled, the quasar shuts down. The galaxy continues existing, but the brilliant central engine goes dark. The black hole remains dormant, waiting for new material to fall in. Our own galaxy once hosted a quasar. Evidence suggests the Milky Way's central black hole consumed gas vigorously billions of years ago. The quasar phase ended when the fuel was depleted. Now the black hole sits relatively quiet, occasionally flaring when a star wanders too close or a gas cloud falls inward. Webb's ability to detect distant quasars helps constrain how quickly supermassive black holes grew in the early universe. Each quasar discovery at high redshift pushes back the timeline for when these monsters became active. The data suggests black hole growth happened faster than standard models allow, adding to the mystery of early structure formation. What makes quasars especially valuable for studying the universe's scale is their visibility across enormous distances. A quasar billions of light-years away can be detected because it shines so brilliantly. Galaxies at similar distances might be too faint to see, but quasars announce themselves clearly. This means quasars serve as markers for the universe's extent. The most distant quasars define the frontier of observable space. And when galaxies collide, something even more spectacular occurs. Webb captured images of galaxies in the process of merging. 2 massive collections of stars, gas and dark matter rushing toward each other at speeds measured in millions of miles per hour. When they meet, the collision transforms both. Despite the violence, individual stars rarely collide. Space inside galaxies is mostly empty. Stars are separated by vast distances. When 2 galaxies merge, their stars pass through each other like 2 swarms of gnats interpenetrating. The stellar populations mix, but direct stellar collisions are extremely rare. Gas behaves differently. Gas clouds from the 2 galaxies do collide. They crash together at tremendous velocities, creating shock waves that compress the gas to extreme densities. This compression triggers massive bursts of star formation. Thousands or millions of new stars ignite within a few million years. The merger region blazes with the light of newborn stellar populations. Webb observed one merger in particular that showcases this process. 2 galaxies designated as ARP 107 show a dramatic collision in progress. The larger spiral galaxy is being disrupted by a smaller elliptical intruder. The impact has created brilliant knots of star formation, visible as bright blue regions in ultraviolet light appearing red in Webb's infrared view due to redshift. The tidal forces during a merger are immense. Gravity pulls stars and gas into long streamers extending hundreds of thousands of light-years from the main bodies. These tidal tails eventually fall back into the merger remnant, but they create striking visual features during the collision process. Simulations show that major mergers between similarly sized galaxies produce elliptical galaxies. The ordered structure of spiral arms gets destroyed. Stars end up on random elliptical orbits around the merge center. Gas falls toward the core, where it either forms stars or feeds the central black hole, creating an active galactic nucleus. The Milky Way is heading toward a merger with Andromeda. The two galaxies are approaching each other at about 250 miles. In approximately 4 billion years, they will collide. The merger will take several billion years to complete as the galaxies make multiple passes, gradually spiraling together due to gravitational interactions and energy loss. When the Milky Way and Andromeda merge, Earth's night sky will transform. Andromeda will grow larger in apparent size as it approaches, eventually filling a significant portion of the sky. During the merger itself, newly formed star clusters will blaze across the heavens. The combined galaxy, sometimes called Milk-Dromeda, will be an elliptical containing all the stars from both progenitors. Webb also detected mergers in the very early universe, galaxies colliding when the cosmos was less than 1 billion years old. These early mergers might explain some of the unexpectedly massive galaxies found at high redshifts. Instead of growing gradually through steady star formation, galaxies could build mass quickly by merging with neighbors. The merger rate was higher in the past. The universe was smaller and denser. Galaxies were closer together. Collisions happened more frequently. As cosmic expansion continues, galaxies separate. The merger rate declines. In the far future, galaxy mergers will become increasingly rare. As dark energy pushes galaxy groups farther apart, every major elliptical galaxy likely resulted from at least one major merger in its past. The smooth, featureless appearance of ellipticals reflects their violent origin. The chaos of collision erased any organized structure, leaving behind a gravitationally relaxed system where stars orbit on random paths. Mergers also affect star formation in unexpected ways. Sometimes they trigger bursts, but sometimes they shut down star formation entirely by heating gas to temperatures too high for collapse. Webb captured one of the most striking examples of gravitational lensing ever photographed, a perfect ring of light surrounding a massive foreground galaxy. This phenomenon is called an Einstein ring, predicted by Einstein's theory of general relativity decades before anyone observed one. Gravity bends space. Massive objects create curves in the fabric of space-time. When light travels past a massive object, it follows these curves. From our perspective, the light's path appears bent. The effect is called gravitational lensing because massive objects act like lenses, focusing and distorting light from background sources. When the alignment is perfect, extraordinary things happen. If a distant galaxy, a massive foreground galaxy, and Earth line up precisely, the background galaxy's light gets bent into a ring shape around the foreground object. Every photon from the background galaxy that passes on one side of the foreground mass gets deflected toward us. The same happens on the other side. The result is light arriving from all directions around the lensing galaxy. The ring isn't actually circular, it's a sphere. We see it as a circle because we're looking at a three-dimensional effect projected onto our two-dimensional field of view. If you could move above or below the alignment, you would see the ring at an angle, appearing elliptical. Einstein rings are rare. They require nearly perfect alignment between three objects separated by billions of light years. Most lensing events create arcs or multiple images instead of complete rings. When a ring does form, it provides powerful scientific opportunities. Scientists use Einstein rings to measure the mass of the lensing galaxy. The degree of bending depends on how much mass causes the deflection. By analyzing the ring's radius and the known distance to the background galaxy, astronomers calculate the total mass of the foreground object, including dark matter. These measurements reveal that dark matter extends far beyond visible galaxy boundaries. The Einstein ring size indicates how far dark matter halos reach into space. Typical results show dark matter distributed in a roughly spherical halo surrounding the luminous galaxy, with mass concentrated toward the center and declining gradually outward. One Einstein ring captured by Webb shows a galaxy that existed 13 billion years ago, lensed by a foreground galaxy only 4 billion light-years away. The background galaxy appears magnified and brightened by the lensing effect. Instead of appearing as a faint smudge too dim for detailed study, it shows up as a bright ring where scientists can analyze spectral features and measure star formation rates. This magnification effect turns massive galaxies into natural telescopes. They boost the light from objects behind them, making those distant galaxies easier to study. Without lensing, many high redshift galaxies would be too faint for Webb to observe in detail. Lensing brings them into view. Galaxy clusters create even more dramatic lensing. The combined mass of hundreds or thousands of galaxies, plus hot plasma plus dark matter, creates strong gravitational fields. Background galaxies get stretched into long arcs. Some appear multiple times as light takes different paths around the cluster. The resulting images look bizarre, with galaxies warped into crescent and elongated streaks. Webb used this effect deliberately. Scientists pointed the telescope at known massive clusters, knowing that the clusters would magnify background galaxies. This strategy revealed some of the faintest and most distant galaxies ever detected. Objects that would be invisible without lensing became observable through the cluster's natural magnification. The most extreme lensing can magnify background objects by factors of 10 to 100. This turns the study of very distant galaxies from impossible to feasible. And what scientists see when galaxies enter dense environments reveals dramatic transformations. When a galaxy falls into a massive cluster, it doesn't gently settle into orbit. It plunges through the cluster at speeds reaching millions of miles per hour. During this passage, the galaxy encounters a hostile environment that tears away its gas. The space between galaxies in a cluster isn't empty. It's filled with extremely hot plasma heated to tens of millions of degrees. This intergalactic medium is thin by Earth standards, but substantial on cosmic scales. When a galaxy moves through it at high velocity, the galaxy experiences resistance similar to a car driving through water. This resistance is called ram pressure. Imagine sticking your hand out of a moving car window. Air pushes against your hand even though you're moving through the air rather than air moving past you. Gas in galaxies experiences the same force when the galaxy moves through the hot cluster plasma. The ram pressure strips gas from the galaxy. Observations show long tails of gas streaming behind galaxies as they plunge through clusters. These tails can extend for hundreds of thousands of light years, containing enough material to build millions or billions of stars. Instead, the gas gets left behind in the cluster environment. Without gas, the galaxy cannot form new stars. Star formation requires cold gas that can collapse under gravity. Once a galaxy's gas is stripped away, star formation stops within a few 100 million years. Existing stars continue shining, but no new ones replace those that die. The galaxy transforms from a blue star-forming spiral into a red quiescent elliptical or lenticular. Webb detected numerous examples of this process, called environmental quenching. Galaxies in clusters show much lower star formation rates than similar galaxies in less dense environments. The difference is dramatic. A galaxy in isolation might form several solar masses worth of new stars per year. The same galaxy after falling into a cluster might form zero. The effect is especially pronounced for smaller galaxies. Massive galaxies have deeper gravitational wells that hold onto their gas more effectively. Small galaxies have weaker gravity. Ram pressure can strip away their entire gas content in a single passage through the cluster core. They become red and dead, containing only old stellar populations with no ongoing star formation. One image from Webb shows a galaxy nicknamed the Jellyfish Galaxy. As it falls through its host cluster, ram pressure strips long tentacles of gas and stars trailing behind the main body. Star formation continues in these tentacles for a brief period before the gas dissipates completely. The galaxy leaves behind a trail of star clusters, marking its path through the cluster. Tidal interactions also play a role. The combined gravity of the cluster and neighboring galaxies pulls on the infalling galaxy. These tidal forces can strip away outer stars, leaving behind a smaller, more compact remnant. Over billions of years, large spiral galaxies that fall into clusters can be reduced to small elliptical galaxies through this stripping process. The cluster environment also prevents galaxies from accreting new gas from intergalactic space. In isolation, galaxies continuously draw in fresh material from surrounding cosmic web filaments. This replenishes gas consumed by star formation. In clusters, the hot intergalactic medium is too energetic to be captured by individual galaxies. The supply of fresh gas gets cut off. Scientists estimate that approximately half of all galaxies in the universe reside in groups or clusters. This means environmental effects influence the evolution of a huge fraction of the galactic population. Understanding how environment shapes galaxies is crucial for understanding galaxy evolution as a whole. And across cosmic time, these environmental effects have changed the chemical composition of everything that exists. The early universe contained almost nothing but hydrogen and helium. These are the two lightest elements, formed in the first minutes after the Big Bang. Everything else came later, forged inside stars and scattered through space when those stars died. Webb detected this evolution by analyzing the spectra of galaxies at different distances. Nearby galaxies show spectral lines from many elements: carbon, oxygen, nitrogen, iron, silicon, magnesium. The full periodic table appears in their light, but the most distant galaxies show primarily hydrogen and helium, with only traces of heavier elements. This pattern reveals how the universe has been enriching itself with heavy elements over billions of years. The technical term is metallicity. Astronomers call anything heavier than helium a metal, even though elements like oxygen and carbon aren't metals in the chemistry sense. Low metallicity means few heavy elements. High metallicity means abundant heavy elements. The first stars formed from pure hydrogen and helium. When these massive stars exploded as supernovae, they ejected newly created heavy elements into surrounding space. The next generation of stars formed from gas enriched with these elements. When those stars died, they added even more heavy elements. Each stellar generation increased the metallicity of available gas. Scientists measure this by examining absorption and emission lines in galaxy spectra. Specific elements produce characteristic patterns. Oxygen creates lines at particular wavelengths. Carbon creates different lines. By measuring the strength of these lines relative to hydrogen, astronomers determine how much of each element exists in the gas. Results show that metallicity increases steadily from high redshift to low redshift. Galaxies at redshift 8 show metallicities around 2% of what we observe in nearby galaxies. Galaxies at redshift 4 show 20%. Galaxies at redshift 2 show 50%. By redshift 0, meaning the present day, metallicity reaches current levels. This enrichment is crucial for planet formation and life. Planets require heavy elements. You cannot build a rocky world from hydrogen and helium alone. Carbon-based life needs carbon, obviously, plus nitrogen, oxygen, phosphorus, and other elements. Early generations of stars provided the raw materials for everything more complex than hydrogen gas. Our Sun is a third-generation star at minimum. It formed from gas already enriched by previous stellar generations. That gas contained the silicon, iron, oxygen, and other elements needed to build Earth and everything on it. Every atom in your body, except hydrogen, was created inside a star and released through a supernova or stellar wind. Webb's observations show this enrichment proceeding faster in some environments than others. Dense regions where stars form rapidly accumulate heavy elements quickly. Sparse regions where star formation proceeds slowly remain metal-poor longer. Galaxy mergers accelerate enrichment by triggering intense starbursts that produce and disperse heavy elements rapidly. The most metal-poor galaxies Webb detected exist at high redshifts. These pristine systems contain gas that has experienced minimal stellar processing. Studying them reveals what the universe's raw material looked like before significant enrichment occurred. The composition matches predictions from Big Bang nucleosynthesis, the process that created elements in the first minutes after the Big Bang. Even in galaxies poor in metals, certain elements rise faster than others. Oxygen, for example, accumulates more quickly than iron, not by chance, but because stars forge elements on different timelines. Massive stars burn bright and die young, seeding space with oxygen when they explode. Smaller stars live longer, quietly building iron over billions of years. The balance between oxygen and iron becomes a record of a galaxy's star-forming past. By tracking metallicity across cosmic time, scientists piece together the universe's chemical story from an early expanse made almost entirely of hydrogen to a cosmos where heavy elements form just a few percent of all matter. Yet that small fraction changed everything, making planets, complex chemistry, and eventually life itself possible.